Hi, I am Emerson D. Kumlat. In this video, I am going to present my Module 2 machine problem. I will be implementing my chosen numerical method technique on a programming platform. I have chosen topic set 3, which is create Simpson's rule, and topic set 5, which is forward divided difference truncated plus Richardson Extrapolation. I'll be using the C++ as my programming platform, which is the most popular programming languages available. C++ is a high-level general-purpose programming language created by Danish computer scientist Bjarne Stroustrup in 1985. Python is a high-level programming language that is known for its simplicity and readability. It was created by Guido van Rossum and first released in 1991. We will implement the numerical method technique, forward divided difference, and Richardson's extrapolation on this programming platform. We will implement the numerical method technique, create Simpson's rule on the C++ programming platform. The C++ can be accessed online using any web browser through this link. On this case, we don't need to install the C++ software on our laptop to run the application. Let's begin with the first topic, which is the create Simpson's rule. Simpson's rule is a numerical integration technique used to estimate the definite integral of a function over a given interval. The method is named after the mathematician Thomas Simpson. In this rule, you divide the interval into subintervals and use quadratic approximations over 3 consecutive subintervals at a time. The basic idea of Simpson's rule is to approximate the area under a curve by using a series of parabolic or quadratic approximations as seen on the graph. The 3/8 Simpson's rule is a specific variation of 1/3 Simpson's rule that is used when you have equally spaced data points and the number of data points n is a multiple of 3. The formula for 3/8 Simpson's rule can be expressed by this function, whereas f of x of I are functions that are not multiples of 2. F of x of j are functions that are multiples of 3. F of x of O is the initial function, and f of x of n is the last function n. This is the algorithm of the program. First of all, we need to define the function f of x in our program that we need to integrate. Then, in the second step, we get the user inputs regarding the initial and final limit of the integral. That is a and b. A will be the initial limit and b will be the final limit or the endpoints of the interval. Then, we need to have the number of intervals, which is n. The n should be a multiple of 3. Then in the third step, we will calculate the h interval, that is the difference between a and b divided by the n. Fourth step, we set sum as 0. Then we begin to evaluate function from I is equal to 1 to n minus 1. Begin for I is equal to 1 to n minus 1. Set x is equal to a plus h multiplied by I. If I sub 3 is equal to 0, then set sum is equal to sum plus 2 multiplied by the function of x. Else, set sum is equal to sum plus 3 times function of x. And 4, set sum is equal to sum plus f of a plus f of b. Set answer is equal to sum multiplied by 3h over 8. End. Here is the flowchart representation of the program raised from the given algorithm. Let's have a polynomial function example that we will use on the program. Estimate the integral of the given function from x is equal to 0 to x is equal to 0.8 using Simpson's 3/8 rule. A function of x given is equal to 0.2 plus 25x minus 200x squared plus 675x cubed minus 900x raised to 4 plus 400x raised to 5. Let's proceed with the program self-simulation using the C++. This is an online C++ compiler. I have here the source code. As you can see, we include some of the basic libraries including the CMath. We define the function here. The program is set to display 5 units decimal places. Let's run the program. The program will ask you first for the initial limit a. In our example, it is 0. Then it will ask you for the final limit. In our example, it is 0.8. Then We also need to enter the number of subintervals. It should be a multiple of 3. We use n segment as 12 in our example. When we hit enter, the program will print the definite integral results, which is 1.64006. It would have been more accurate if we had used a higher number of n segments. Let's try to use the same program using a transcendental function example. Estimate the integral of the given function from x is equal to -1 to x is equal to 4 using Simpson's 3/8 rule with n is equal to 99 segments. The function of x given is 3x plus sine x minus e raised to the x. On the source code, I have already defined the function 3x plus sine x minus e raised to x. The program is set to display 5 units decimal places. Let's run the program. The program will ask you first for the initial limit a. In our example, it is -1. Then it will ask for the final limit, which is 4. Then we also need to enter the number of subintervals. We use n segment as 99 in our example. When we hit enter, the program will print the definite integral results, which is -30.53622. Checking in the calculator, it will give you the same results. Thus, this program is effective in calculating the value of a definite integral for both polynomial and transcendental functions. That's how the program for 3/8 Simpson's rule using C++. Let's move to our second topic, which is the forward finite divided difference, a method used in numerical analysis and numerical differentiation to estimate derivatives of a function using data points. It is a variant of the finite divided difference method, where the focus is on estimating the derivative at a specific point by utilizing data points ahead of that point. This method is particularly useful when you have data points that are collected in a forward manner, and you want to estimate derivatives at points further along the data sequence. The formula for FFPD truncated can be expressed as f prime of x sub I is equal to f of x sub I plus 1 minus f of x sub I all over h, where f of x sub I plus 1 function from the reference point plus 1 step size. F of x sub 1 is function from reference data point. H is the step size. Let's have a polynomial function example that we will use on this program. Estimate the derivative of the function at x of I is equal to 0.5 using forward finite divided difference at the step size h is 0.5, applying the truncated formula. Function of x is equal to -0.1 x raised to 4 minus 0.15 x raised to 3 minus 0.5 x raised to 2 minus 0.25 x plus 1.2. Let's try and execute this example onto our program. On the online compiler, we select the language Python 3. Copy and paste the code. The function is f is declared on the first row. We interpret the function according to the format that the program can understand. We then state the values of x, which is 0.5 in the given, and h is 0.5. We declare the value of the differential equation at step size 1, which is 0.925, and declare the value of differential equation at step size 1, which is -0.9125. We then ask the program to print the truncated output dh of 2, dh of 1. The formula for the forward difference is stated. Thus, the final answer will be -1.154688 and -1.45. Let's move to our final topic. Richardson's extrapolation is a numerical method technique used to improve the accuracy of a numerical approximation, particularly in the context of numerical integration or differentiation. The basic idea behind Richardson's extrapolation is to use two or more numerical approximations of a quantity, each with a different level of accuracy, that is, using different step sizes, and combine them to produce a more accurate estimate. The formula is given as d is equal to 4/3 of d of h of 2 minus 1/3 d of h of 1. Let's have an example. Improve the derivative estimate of the function at x of y is equal to 0.5 using Richardson's extrapolation on the forward finite divided difference as step size h is equal to 0.5 and h is equal to 0.25. The function given is negative 0.1 x raised to 4 minus 0.15 x raised to 3 minus 0.5 x raised to 2 minus 0.25 x plus 1.2. Let's try and execute this example onto our program. On the online compiler, we select the language Python 3. Copy and paste the code. We have to declare on the program the values of the four finite difference functions, which is negative 1.45 and negative 1.15469. We then write the formula d, which is 4/3 times ffd2 minus 1/3 ffd1. Then, the program will display the Richardson's extrapolation result, which is negative 1.05625. That's how the program for forward finite divided difference and Richardson's extrapolation using Python. These are my references. Thank you.